Welcome to the opening seminar of the fall 2025 season of the GEOTOP seminar. It is my great pleasure to host the seminar today and to welcome Professor Ginestra Bianconi from Queen Mary University of London, who's going to speak to us about her recent work on how topology shapes the dynamics of higher order networks and more. Ginestra, I'm looking forward very much to your talk, and the floor is yours.
Thank you so much for the kind invitation. It's a real pleasure to speak at GEOTOP seminar series. Today I want to bring you on a journey on topics that we have covered in these last 5 years together with a large group of students at QMUL and alumni and a very large network of dear collaborators in international universities. So in these last 20 years, networks are emerging as the more modern fundamental approach for complex interacting systems. Before that, during the century, people have pursued intensively a reductionist approach, looking for the fundamental element of nature and the fundamental interaction. But yet it has been realized that this reductionist approach, considered in the traditional way, is not suitable to study complex systems such as the brain or the cell. And from this realization, it emerged the field of complexity and network science. But I would say, a bit controversially, that network science and network theory is developing as another type of reductionist approach, in which of all the detail of a complex system, one only retains the network of this interaction. And from this topology of the network, one wants to understand the dynamics. So the object of study is not the interaction in se, but is the relation and the set of the complex interaction and the geometry and the topology of these networks. Yet the networks have been very successful in studying complex systems in the last 20 years, but they have a limitation in the sense that they encode only pairwise interaction. And in order to go beyond this limitation, we need higher order networks, which reveal also the higher order or many-body interaction in a complex system. And in doing so, they reveal also the topology and the geometry of the data. A beautiful example of higher order networks are collaboration networks, where you can have, for instance, more than two authors co-authoring the same paper, which is familiar to all the scientists. But higher order brain networks are also raising a lot of attention, and both at the level of the neuronal interaction, but also at the level of brain region, it is emerging that is really important to consider higher order network. For instance, like let's say in a very general term, if you have three regions of the brain, they might be interacting pairwise and with the time series that are correlated pairwise, but actually they might also have a many-body interaction. For instance, they can be activated at the same time, and this change the picture of our understanding of these dynamics. In the last 10 years, I would say, there has been very many breakthroughs in understanding this interplay between topology and dynamics, and as our host has been playing a very crucial role in this respect. And actually, so the idea and the realization is that actually topological methods can help us reveal phenomena and aspects of the dynamics of brain networks which cannot be revealed by more traditional combinatorial approach. They're not only simplices and hyper-edge in complex system. There are also other type of higher order interaction, such as triadic interaction, where you can have one node or more nodes modulating the interaction between other two. And this occurs, for instance, in brain network, where you can have two neurons interacting via a synaptic signal, but then you can have the presence of a glia which directly modulate these synaptic signals. And this leads to this interesting role of this triadic interaction in shaping the dynamics. And we have launched a very extensive research direction in studying triadic interaction and its effect in dynamics. And in particular, we show that the giant component itself, as you see in functional and MMRR movies, can become a dynamical variable. And so the critical phenomena such as percolation can be a fully fledged dynamical process in which the size of the giant component can undergo even a root 2 chaos and a period doubling transition. From the study of higher order network, it emerged a complexity challenge, and this is to combine our description, topological and geometrical description, with insight on the network dynamics. And this interplaying, possibly we want to interpret in the light of information theory to have a better theory of complexity, which can shed light into brain research, physics itself, and a new formulation of artificial intelligence algorithm. So at the beginning of this research line, I wrote a book by Cambridge University Press in which I provide a general view of the interplay between topology and dynamics. And from this reflection, it emerged that actually this important interplay between structure and dynamics, which has been the focus of network theory for so many years, is not only shaped by combinatorial and statistical property. So for instance, the degree distribution shapes the property of epidemic spreading on a network, but also simplicial topology and simplicial geometry are fundamental to describe this interplay between structure and dynamics. And I would like to focus on topology first and then tell you something more about geometry at the end of the talk. So in order to study this, we have data set, but we have also reliable model of simplicial complexes, both model of emergent hyperbolic geometry, growing simplicial complex model, and model maximum entropy model, configuration model of simplicial complex that we have developed during the year, and whose code are available in my GitHub page. And given this network, we can study how this interplay between topology and dynamics and the work of this last recent year is summarized in this nature physics perspective that is being published this year. And the code and the supplementary information are available at this GitHub repository. So what is topology? Topology is the study of shape and their invariant. So for instance, Betti numbers, which characterize the number of connected components, the number of cycle, the number of two-dimensional holes. And if you have a network whose structure could be the structure of this fungi network here, it is clear that just this cycle structure is important. So you want to maybe characterize the structure with topology, and they are very important and reliable tool to do that, like a persistent homology. But actually here I want to tell you about the use of topology to study dynamics. And it is becoming clear that we need to go behind the node-centered point of view, in which the dynamical variables are only associated to the node of the network, and we need to embrace a topology also from the dynamical point of view, and associate topological signals, so dynamical variable, also to the edge or to the triangle of a simplicial complex. And these topological signals include data such as synaptic signals, edge signals in the brain as proposed by Olaf Sporns, citation of a collaboration network that can be, for instance, a function associated to a simplex. So for instance, how many citations three authors get in their paper co-author together. And you can have also vector field, such as speed of wind, a given location on the surface of the Earth, that you can project on a tessellation of the surface of the Earth and treat it as this topological signal. So mathematically speaking, you can treat it as cochains. So if you have, for instance, a simplicial complex formed by node, edges, and triangle, you can therefore encode the dynamical state into what we call a topological spinor, which is the direct sum of a 0 cochain, 1 cochain, and 2 cochain. So it's a vector which includes the dynamics of node, edges, and triangle. And with this description of the dynamics of a network, you can use tool of discrete stereo calculus. So for instance, if you have a function on the node, you can do the gradient, the difference of the function on the two-end node of a link, and you can associate it to the link. Or if you have a function defined on the links, you can do flux in and minus flux out, and you can associate the divergence to the node. Or you can do the circulation and you can associate the associated curl to the triangle. And all these transformations are linear, so they are encoded in linear operator that can be represented as rectangular matrices between node and links and triangle, and so on. And these matrices really represent you discrete divergence, discrete gradient, and discrete curl. And by contracting this matrix, you can get Hodge Laplacian, and the Hodge Laplacian describe higher order diffusion. So for instance, you can have the one Hodge Laplacian, which describe diffusion from edge through edge, going either through node or through triangle. And then I don't have to say here that this Hodge Laplacian have a beautiful connection with topology, because the dimension of the kernel of the n-Hodge Laplacian is the n-Betti number. So it will tell you how many holes of dimensional n you have in the simplicial complex. Interesting, also the eigenvector structure is important and relevant. So we know that for the graph Laplacian, the harmonic eigenvector are constant on each connected component. So they reveal the connected component. And the one Hodge Laplacian are localized around the one-dimensional holes. So there is a basis in which they identify one holes. And from the study of the Hodge Laplacian, there is this beautiful result of Hodge decomposition, in which you have an edge signal, for instance, which can be decomposed uniquely into a gradient flow, an harmonic component, and a curve flow. So how can we use that to study dynamics? And we started with the synchronization property, and particularly the Kuramoto model, in which the standard formulation proposed by Kuramoto is that practically you have a phase oscillator on each node, each one with a different frequency, and drawn from a Gaussian distribution, and you couple them to each other via the edge, via the links, and such a way that a phase tries to align with a nearby phase. And when the coupling constant of this interaction is above a threshold, you have this phase transition in which a finite fraction of the nodes trying to starting to oscillate together as measured by this order parameter. And then together with Ana Paula Millán and Joaquin Torres in 2020, we start asking ourselves, can we define a topological higher order Kuramoto model coupling higher order dimensional topological signals? So what happens if these phase oscillators are associated to the edge or to the triangle? And in order to study that, we realized that actually the standard Kuramoto model can be written in terms of the boundary operator. And from this realization, it was immediate to write and formulate the topological Kuramoto model, in which you have, for instance, the phases associated to the edge. You project, for instance, on the triangle doing the curl, you apply a nonlinear transformation, and then you project from the triangle back to the edge. And you can do the same projecting to the node and then from the node to the edge. So you have this linear transformation, nonlinear transformation, and linear transformation structure, which is actually the core also of the algorithm of simplicial neural network algorithm that have been proposed after our formulation of the topological Kuramoto model. And they have a similar nature structure. So this topological Kuramoto model helps us also having a new vision of this traditional Kuramoto model. So the traditional Kuramoto model, if we formulate in terms of the boundary operator, we can project on the harmonic eigenvector of the graph Laplacian, and we see that this harmonic mode oscillates at the frequency dictated by this intrinsic frequency. So it's free to oscillate at the frequency put by end, and is not affected by the coupling constant. So what happens, and this is uniform on each connected component. So what happens in synchronization is that all the other modes increasingly freeze, and what is left ideally when all of the other modes freeze is this free dynamics, which is uniform on each connected component of the network. So for the topological Kuramoto model, something happens that is similar mathematically, but different in different phenomenology, because what we have is that now the harmonic mode of the dynamics, for example, defined on the links, is free to oscillate. So this will be localized on the holes, will not be now uniform on the connected component, but localized on one hole or the other. So you see, if the synchronization happens and all the other mode freeze, the dynamics that is left learn the topology and localize around the holes. So on some point of view, the topology shapes the dynamics, drives the dynamics. On the other point of view, the dynamics learn the topology. And we can have a point of view also Hamiltonian, in which these phases are oscillated with their intrinsic frequency, but then the coupling comes from the gradient of an Hamiltonian. And for the standard Kuramoto model, this is the XY Hamiltonian. And for the topological Kuramoto, this is a new topological Hamiltonian, which has many minima, as the number of holes. And so the dynamics can be in one hole or the other, or in a linear combination of those. And actually here an important point arises if we were to interpret these dynamics for something that could be relevant for the brain. We would like to associate the localization in one hole and another in terms of information theory as capturing some attractor or some memory in the system. And actually we would like to devise way to control and induce the localization in one hole and in the other. But this is, for the moment, still a research question. So this is what happens where the two holes are empty. We can have also one hole fills and the other empty, and there are ways, order parameter, that detect the difference between the two. And if the two holes are both filled, there is no dynamics left anymore in the I coupling constant regime. So this is what happens in terms of the harmonic eigenvector. Let's look at what are the other modes doing. So we can project the other mode into triangle or into node and study the projected dynamics that now completely decouple. And then we have this dynamics of the irrotational mode and solidonial mode, which show the freezing or synchronization that is occurring. So the freezing of the solidonial component, the freezing of the rotational component, and then the synchronization occurring in the harmonic component, that is the one that is left. And these occur at zero coupling synchronization threshold. But if we modulate now the part of the dynamics that is projected on the triangle with the order parameter of the dynamics projected on the node, we find that these two coupled projected dynamics, these two projected dynamics are now coupled, and the synchronization becomes discontinuous and explosive. So we have a synchronization that occurs at non-zero coupling constant value. And this is what happens on the configuration model of simplicial complex. We see a similar behavior also on real data of connectome. So this is numerical result. And of course, we want to also have analytical prediction. The Kuramoto model is very well known to be quite challenging to get analytical result if we go away for a fully connected network. But there are reliable approximations, so we extended the annealed solution to the topological Kuramoto model defined on Poisson network or scale-free network, and we have a beautiful agreement with the simulation result, as you can see. So here I show that actually the dynamics learn the topology, and the topology shapes the dynamics, because the topology will localize on one hole or the other hole of the network. But actually, a question that raised, and we raised this question together with Timoteo Carletti and Lorenzo Giambaglia, and then work with Runye Wong and Riccardo Muolo, is can we have global topological synchronization? So for instance, an edge signal in which all the edges of the network are actually dynamically oscillating at unison. So for tackle this problem, we need to formulate another theoretical framework of couple identical oscillator coupled via the Hodge Laplacian. So the dynamics now can be chaotic or very general, but the coupling is the one defined by the Hodge Laplacian. And here the scenario is similar in the sense that you can have synchronization if all the signals are aligned with the harmonic eigenvector, and but the harmonic eigenvector is localized on the holes. So in general, we'll have one hole here, one hole there. So we will not have a global synchronization because the whole will not span the entire structure. In order to have global topological synchronization, we might need to have whole that span the entire structure and that make the constant eigenvector, the harmonic eigenvector becoming the constant eigenvector on all the edge. And this occurs, for instance, on very particular and symmetric structure like the square lattice tessellation of the torus, in which you have that the harmonic eigenvector it can be constant on all the edge, on all the square, or on all the nodes. So maybe I can stop here if there are any question or.
Please unmute yourself if you have any questions. Feel free to ask.
Yes, Ginestra, Renzo here. I have of course, I'm not in the field specifically, and so forgive me for very simple questions. Suppose I consider, as part of my work indeed, a system of fluid vortices, for example, that are decaying like in turbulence, I suppose. Can we regard each structure, each vortex as a topological state, and then consider transition from one topological state to another, as the approach I and collaborators of mine have proposed and are proposing? But then the question is, can I regard the topological states, for example, vortex knots and links, as nodes in your network?
No, for the moment here, the nodes are structural nodes, so there's a big distinction between what is structure and what is dynamics. But yes, this is an interesting point of view. Yeah, but it is a bit of a different approach, I think.
Mm-hmm. And I'm very intrigued by a number of things you said, and I have a hard time, of course, not being in the field specifically, to fit aspects that are deterministic, and for example, energy minimization or some optimal path dictated by some sort of energy minimization, and the randomness typical of some phenomena, for example, reconnection in structures, in fluid structures, that are totally unpredictable. So is there any way you can just suggest to combine these two things in one whole picture?
Yes, of course. I'm a statistical mechanics person, so I like stochasticity, but in this talk there will be no. So, yeah, one needs to start from somewhere, and possibly is a good research question. Yeah.
Okay, thank you.
Thank you, Renzo. So, Ginestra?
Yes. So until now we have seen these topological signals having a collective behavior, so that these topological signals are defined on node, edges, triangles, and so on. And then the question is, can we treat and process topological signals of different dimensions together? So for this, we need Dirac legacy and what is called the Dirac operator, which allows us to study interacting topological signals of different dimensions and coexisting in the same network topology. So we have this topological spinner, including the node signal, link signal, and triangle signal, and we act on it with this Dirac operator. So when we act with the Dirac operator, this allows crosstalk. So if you have for instance, an edge signal, you project on the node and you get the divergence. or you have a node signal you project on the edge and you have the gradient, and then you can allow, you know, this projected signal to crosstalk with the original signal, for instance. So you can allow crosstalk between signals of different dimension. And this is a beautiful property that is not shared with the Hodge Laplacian, that instead couple edge signal with edge signal exclusively, for instance. So why is this the Dirac operator? Because as Dirac proposed the Dirac equation as the square root of the Klein-Gordon equation, the Dirac operator can be considered as the square root of the Laplacian, in particular the Gauss-Bonnet Laplacian, which is a matrix which is in the diagonal as the Hodge Laplacian, the graph Laplacian, the one Laplacian, the two Laplacian. So this is a beautiful property of the Dirac operator. And for the moment, we have defined this only topologically, but we can include also geometry. So we can include a discrete geometry which describes the scalar product among cochain, which leads to a weighted Dirac operator eventually. So with this Dirac operator, we can go back to physics and ask whether we can construct topological Dirac equation in the spirit of the Dirac-Kahler equation proposed in the continuum and in the staggered fermions. And the answer is yes, we can. We can write a topological Dirac equation. Was Hamiltonian is the Dirac operator plus m gamma, and gamma is a matrix that anti-commute with the Dirac operator. So we can study the eigenstate of this topological Dirac equation, which boils down in writing an algebraic equation for this eigenstate. And this eigenstate follows a relativistic dispersion relation in which instead of having the momentum, you have the singular value of the boundary operator, and m plays the role of the mass. And so you have, you know, for any singular value of the boundary operator, you have positive energy state and negative energy state. But so you have this symmetry between what is called matter and antimatter, but this symmetry is broken at the level of harmonic mode, because we know that the harmonic mode have a degeneracy that is given by the Betti numbers. So the state that will have energy E equal to m, which correspond to a singular value 0 of the boundary operator, and they are associated to state defined on the nodes, will have a degeneracy given by the Betti number beta 0, while the energy state at energy minus m will have a degeneracy given by the Betti number beta 1. So if you write the spectrum of this Dirac operator of an arbitrary network, you find this beautiful symmetric structure that is then broken at the level of the harmonic signal. So I'm a big promoter of the use of this Dirac operator in complexity and in AI. And so this allows, as you see, the signal of different dimensions to interact to each other. And we launched a program studying Dirac synchronization, Dirac Turing pattern, topological Dirac synchronization. And just to have a flavor, you can have this global Dirac synchronization in which you can have node, edge, and square that now oscillate together in this square lattice tessellation of the torus, and leading to this very symmetric and very regular dynamical state. But this is not possible in any arbitrary state. So this is one of the few possible topology which allow this very beautiful symmetric state. A question that arises and can be tackled with the Dirac operator is whether we can have synchronization along also non-harmonic mode. And can we design synchronization that as a pattern that is not along an harmonic mode. And this is work with Ahmed Zaid, which is my student. And in this work, what we do is we can define this Dirac equation synchronization dynamics, in which we have a topological spinner. So the phase on node and links, for instance, oscillating with their intrinsic frequency defined on node and links, but then interacting via gradient flow of an Hamiltonian, which now is minimal over the eigenstate of the Dirac equation, which is actually a very nice and beautiful decomposition of the eigenmode on a network or on a simplicial complex. And the beauty is that we can tune E and M in order to have the synchronization aligned to different eigenstate of the network. So here also, when you look at the dynamics, you see that the dynamics lying along the eigenstate of energy E of the network or the simplicial complex is the one that is free to move. So is the one that remains also if all the other mode freeze. And actually in the paper we study this stability also of this state. But writing this work, we also realized that this is the picture in the spectral domain. But there is also an interesting picture in the real domain. And the interesting picture in the real domain is that if the synchronization is aligned to this mode, in the real space, you actually have a topological cluster synchronization. So practically the phase on the nodes or on the links will oscillate with a frequency which is proportional to the eigenstate of the Dirac equation. So this is beautiful because, for instance, you can apply this to a block model, for instance, in which you have different community of a network. And actually you can select E and M in order to have the frequency in the different cluster oscillating with the frequency dictated by the eigenvector, associated eigenvector. And you can have also the frequency of the bundle of edges that are oscillating at different frequencies. So for instance, for brain dynamics, this could explain, I don't know if it's physical, but could explain different frequency affecting different region of the brain. And the interesting fact is that without touching the topology of the network, just by tuning E and M, we can have, for instance, these two communities, the cyan and the blue, having a relatively similar frequency or having very different frequency, because we just change we align this frequency with a different eigenvector of the Dirac operator. And similarly with the node itself. So this is a beautiful picture that emerged in connection with topological cluster synchronization, which emerged from the real space analysis of this state. So the Dirac operator is also very interesting, and we are promoting that for AI application. And in particular, we have two works on direct signal processing. So if you have in real scenario a true signal defined on node edges and triangle, but you have actually only access to a noisy signal, the goal could be to reconstruct the signal. And in order to do that, so you have the true signal plus a noise, and you have only access to the noisy signal. You want to reconstruct in such a way to minimize this loss function, in which you want to minimize the difference between the reconstructed signal and the noisy signal, because that's your data. Of course, you want to be close to data, but then you include a regularization term. And in this regularization term, you can minimize, the expectation of your of this combination, which on your reconstructed signal, and this combination is such that practically you select you keep from filtering the component that is aligned to the eigenstate of the Dirac equation. So if E is equal to M is equal to 0, actually this kernel reduced to the Gauss-Bonnet Laplacian. So you filter node, edges, and triangle separately, and this is done. But you don't exploit information coming from edge for filtering the information on the node. And interesting, you can have E that is different from 0, and you can learn E from data. And this corresponds, to a filter that instead of filtering mostly the harmonic or close to harmonic component, it filters mostly the component aligned to the eigenstate of eigenvalue E of the Dirac operator. And this allows you to filter and to select, to overcome oversmoothing, and to select a signal that is not smooth, that it can happen in real situation. And the beauty is that you can also use the mass, and so you can do Dirac equation signal processing, and this leads to several improvements, which leads to a much better filtering of real data set, in particular if you iterate the algorithm. And this, you don't need to assume that the true signal is aligned to an eigenstate of the Dirac equation. The true signal can be completely arbitrary, like in this application. And this provides a very important improvement respect to the Hodge-Laplacian signal processing algorithm for some realization of the noise. So the Dirac operator can also be used for doing Dirac persistent homology, so for studying the structure, and this is we apply to biomolecule, for instance. And yes, so we study these to clusterize molecule type, like in this perovskite. And other group have used the Dirac for Dirac-based Gaussian kernel, simplicial attention neural network, and Dirac Bianconi graph neural network in this application. So I reached my conclusion, I think. Network theory unveils the interplay between network topology and dynamics in complex systems, with application to brain research, theoretical physics, and artificial intelligence. And this higher order networks reveal how topology shapes dynamics, and other point of view, how dynamics learn topology. And this Dirac operator is really, I think, very interesting and promising to study both theoretical physics and complexity and AI algorithm. And the next challenge, as I mentioned, is to study this interplay between geometry, topology, and dynamics in the light of information theory. Thank you so much for your attention.
Thank you very much, Ginestra.
Thank you. Thank you very much. A very interesting talk.